In multiple regression, to test for autocorrelation among the residuals, okay, we already looked at ACF and PACF, and we will be using those. Those are more powerful tools. But there is one other test statistic which is very commonly used, and almost all statistical software packages will offer this, and that is called the Durbin-Watson statistic. So because it is popularly used, you need to know about this, but our ACF Durbin-Watson test statistic is only for lag of 1, autocorrelation among the residuals with a lag of just 1. Whereas ACF and PACF, you can compute those for many lags, and therefore those two are more versatile than Durbin-Watson statistic. But since it is part of the statistical packages normally offered, you need to be aware of that statistic. And the hypothesis test that we do with Durbin-Watson is the null hypothesis is that error terms are not autocorrelated with lag of 1, and the alternative being the opposite, that is the error terms do have autocorrelation, again lag of 1. So the test statistic is given by this formula, where you take the residuals minus the residuals of the previous period, and therefore the sum can start only from t equal to 2, because if you start with t equal to 1, then you do not have e sub 0. So you can only start the sum from t equal to 2. So the square of the first lag difference and then the square of the errors themselves. And this ratio gives us the W, and when the sample size is really large, this will approximately be equal to the R sub 1, the autocorrelation lag of 1. Okay, in small samples, this will be different. And the test statistic, there is more elaborate tables available for the DW, but here is the decision rule we'll be using. So DW is close to 0 when there is no autocorrelation, and it will be close to 0 or 4. Okay, the range of values for DW is 0 to 4, and it will be close to 0 when there is no autocorrelation. So that's why we do DW minus 2, and since this can be positive or negative, we take the absolute value of this difference. And then this 3.92 is based on 1.96 for alpha equal to 5%, and then you use the kind of a modified standard error of autocorrelation for lag of 1. So that's where this is coming from. So 3.92 divided by the square root of n. So if this value is greater than this, then we reject, otherwise we do not reject. So let's look at this Durbin-Watson test for our Excel problem. Okay, now let's compute the DW test statistic, and here is the formula. Okay, so we need to look at the residual errors E sub t and lag by 1 period E sub t minus 1. So these are the residuals, and remember we already have the residuals from our regression analysis output. Okay, so here is fitted value and the residuals. So these are the residuals. So let's assemble these residuals first. So that's our E sub t. Okay, so we will copy up to that. Okay, next is we need to lag these by 1 period, so like that, and then find the difference. So E sub t minus E sub t minus 1. So let's copy these two all the way down. Alright, so now we have the raw materials to compute DW. Okay, so let's look at the numerator. So numerator is the squared values of the difference, first difference. So we already have the first difference set up in a column, so all we have to do is to do a sum of squared values of that column. So which is that column. So the difference, and again, is starting from time period t equal to 2 all the way down. So that will give us the numerator, and the denominator is the from t equal to 1 to n sum SQ of the errors themselves. So errors, so which is this column starting from t equal to 1. So now we have the numerator and the denominator. So we find the ratio, and that is our dW. So remember, dW is a value between 0 and 4. Now I have a function like the MAE and MASC function for dW, so we can use the dW function. dW function has two ranges as input. One is the Y range. So we have to go back to the original data now. So we have the Y range is this unleaded, cost of unleaded gas. So, and we need to go only up to that point because that's the estimation sample is what we've used. Okay, and then the second cell range is all the X columns used in the regression analysis. Here we used these 4 X columns, so we have to include all of them. So if they are not together, then you have to put them together. Okay, then we have the DW, Durbin-Watson statistic, and as you see, it's the same number. Okay, so you need to be able to do this in both ways. Okay, now let's look at the number of errors. We'll need this for doing the test. So count of the number of errors we started out with, which is E sub t. How many E sub t's do we have? Okay, so that is our M. Okay. Now testing for significance is null hypothesis is that there is no serial autocorrelation, and the alternative is no, there is correlation. So that's our hypothesis. Now test statistic is the absolute value ABS of dW minus 2. So that's the test statistic. And the critical value that we need to compare that with is 3.92 divided by square root of n. So go 3.92 divided by square root of n. So now if this test statistic is greater than the critical value, we reject, and that is the case. So we reject the null hypothesis. So the conclusion is reject. So that means there is autocorrelation, which is not a good thing because one of the assumptions is that the errors are not correlated. Okay, so when we interpret this conclusion, so we say we have sufficient evidence to conclude the error terms display first order autocorrelation. The probability that this conclusion is wrong is no more than 5%. We're not going to compute p-value here. So when we do have autocorrelation, then we have to take corrective action. So one of the corrective action is to look at the difference. Instead of doing the regression for the Y values, we can do the regression for the difference in the Y values, and we'll discuss those corrective actions later.